All right, let me know what questions you got this morning. Yeah, I've just about got this down for the live streaming. I figured out how to set up the OBX Studio, which kind of found I had an outdated version for some reason that they got on their website. But yeah, audio is about 15 seconds behind. There's not much I can do with that. It's just a network connection issue, but pretty much everything else is set up at this point, so we're good to go. I guess I should tell the summer classes they should thank you for how well this will be going when they have to do their courses online. Yeah, I think the discussion board this week is taking this compound, forming an intermediate, and then you had to form one of these two. You had to identify which was the Markovnikov, which was the anti-Markovnikov, and I gave you a hint that this was an alkene. The mechanism for permanganate reacting with methyl cyclohexane. So I'm not going to go through the full mechanism, but I will talk about the two types of products you can get. I think the mechanism is written out in the notes. It's a fairly complicated mechanism. It's one of those, what's written is probably not actually true. It's probably a far more complicated mechanism. But we've got the 1,2-dimethyl cyclohexene. We're going to react it with potassium permanganate. Now, potassium permanganate is what's called a strong reducing or strong oxidizing agent. So basically what we're going to do is we're going to take carbon, we're going to attach it to something that's more electrophilic than it, electronegative than it is. In this case, it's going to be oxygen. So at low temperature and low concentration, we drive the formation of vicinal diols. Specifically, it's going to be a syn addition. So when we add potassium permanganate to this, at low temperature, high concentrations, we end up getting this compound. So this is going to be a cis 1,2-dimethyl 1,2-dimethyl cyclohexa 1,2-diol. Now, the reason it's a syn addition, when the potassium permanganate reacts on one side of the double bond, because we have this mirror plane, we have the cis-trans symmetry, but we don't actually have chirality because they look the same on both sides. Not chirality. No, wait, we do have chirality. It's just, this will be a mesoform. Now, if we go to high temperature, high concentration, what this is going to do is it's going to break our double bond, and it's going to replace each of them with an oxygen to give us a ketone. So this is why I didn't ask you to name the compound. Naming aldehydes and ketones are general chemistry, or Orgo 2 concepts. So look at our ring. We have 1, 2, 3, 4, 5, 6. So let's draw our 6 carbons. So this one was attached to the double bond, that was attached to the double bond. So carbon 1. We need to add the extra methyl groups. So those are our methyls. And then we're just going to convert our double bonds to ketones. If these weren't methyls, these were hydrogens, these would have been aldehydes. But again, this is more, aldehydes and ketones are very much an orgo-2 concept. But yeah, basic gist here is that if you take potassium permanganate, you actually get both products. If you want to drive just the diol, you have to keep it at low temperature, low concentration. If you want to drive the ketone formation, it's high temperature, high concentration. And this is why in the problem, when you do the separation, you end up getting both. And when you separate, this is more polar than this. So this will do H bonding. So your alcohols will all do H bonding. These only do dipole intermolecular forces. So if we were to run this through a polar column, which is what I said in the problem, this comes out first. So this was band B, and this was band A. Right. Now I do want to talk about I think it's the discussion board problem for either today or it's for Thursday. And this is the 1-propene reaction. So with this problem, and I'll be honest with you, I'd forgotten I'd given you this problem, so it's kind of nice to go back and actually see it with fresh eyes when I go look at these problems. I actually kind of like this problem because it stumped me. It took me about 5 minutes to figure out what I'd actually intended for you to do. I didn't cheat and look at the answer. Like I spent a minute. I was like, why did I specify the alkene? Actually, this was meant to help you as kind of a hint. So it's just a synthesis problem, but it's kind of a guided synthesis problem. So if we look at it, we got 3 carbons here, 3 carbons here, and 3 carbons here. So our carbon backbone here is not going to change. We've still got the 3 carbons. So the question is, how do we go from here to here? And the hint I gave you is that this is still an alkene, which means this functionality doesn't change. So we've still got the double bond. We know we're not adding or subtracting carbons in this step. So the concept here is, well, what would you do? And the big difference here is the Br. So what we need to do in this step is add a bromine to the allylic carbon. So there's actually 2 ways we can go about doing this. One is in bromosuccinimide. So if you don't know what this is, go look it up in the notes. This is kind of a really nice reagent. Actually, it was a joke I made with one of the students I was tutoring in organic a couple of years ago. It was like every answer in their test seemed to be start with NBS, because you had to functionalize the carbon that was beside the double bond. So NBS is nice because it's very specific to the allylic carbons. It's also typically going to give you 1 equivalent of bromine, and that's it. The other option, which isn't wrong, it's just it's harder to control, is if you do a free radical reaction. So we do light and Br2. Now, the intermediate for this step is going to be a free radical. So if we do the light, we end up creating a free radical, and we can get a resonance structure that knocks this double bond back and forth, and that's what stabilizes the allylic radicals. Now, NBS does the same thing. It creates a free radical. It's just that NBS isn't very reactive, whereas the light bromine reaction is actually quite reactive. But regardless, we get the free radical, and we don't get the free radical on the double bond. We only get the radical on the adjacent carbon. And this is where we create the Br. So once you've got this 3 bromo, 1 propene, it should be pretty obvious how to go from here to here. So these are just both addition reactions. You're only adding 1 bromine. So hopefully that'll tip you off as to what the reagent probably is. And I don't remember if I posted in the discussion board or not. The hint is that it's also the same reagent. You're just changing the reaction conditions. So hopefully that kind of helps you out. But what you're trying to do here is derive the Markovnikov versus the anti-Markovnikov. So if we got the double bond here, if we have addition to the most substituted carbon, this is a Markovnikov addition. So we're adding the bromine to the most substituted carbon in the double bond. And, oops, sorry, I drew it twice. This case, where we have the 1,3-dibromo, this is an anti-Markovnikov. So hopefully with these hints you can figure out the discussion board. Pretty straightforward, but I kind of really like this problem. And I do think you couldn't solve it without this alkene hint. But yeah, the big challenge here is actually figuring out how you do the first one. This is actually pretty well fleshed out in the notes in the book about how you would do an addition to a double bond to get the Markovnikov and anti-Markovnikov products. So Christian's asked, for the discussion board, is the mass spectrum graph separate from the synthesis reaction mechanism? Let me bring it up. So that was also meant to be a hint for this problem that I've got up on the board. So that mass spec, if you look at the weight of 3 bromo, 1 propene, it is that mass spectrum. So the idea here was that if you know the mass of 1 propene, so you've got 36, you've got C3H6, 18, it weighs 24 AMUs. The parent ion here, no, that's not right. You had 79. What's up with that one? Did I put up the wrong mass spec? Wouldn't surprise me. That's odd. Probably need to change this problem. Or at least change the EI mass spec. The EI mass spec was supposed to be the help for the alkene to let you know that it was this plus a Br. But what I've got there weighs a lot more than that. Oh, hold on. Carbon doesn't weigh 6. So that's 36 plus 6, which is 42. So this weighs 42. Add another 79 to it. You get roughly 121. And that's what you see in the EI mass spectrum. So bromine's really 79.9. There's a lot of this 79 isotype, 79 and 80 isotope though. So if you look at the EI mass spec, that's what you're getting. So the EI mass spec was to tip you off that this thing, whatever this alkene is, it weighs roughly 79 to 80 AMUs more than the parent compound. So that was supposed to be another hint. Yeah, I tried to help you a lot with this one. I didn't really know how to give you a hint. I just didn't tell you, oh, make this compound. But between it's an alkene and here's an EI mass spec to show you that it gained about 79 AMUs. You're probably adding 1 bromine. Hopefully you can figure it out. So a little bit more review about the allylic hydrogens. So an allylic hydrogen is any, well, we'll start with the allylic carbons. The allylic carbons are any carbons that are adjacent to a double bond. And we typically give them an alpha notation. Now, they stand in a special position next to the double bond because if we add a radical or a carbocation or an electron or a lone pair, we can generate stabilized resonance species. So let's say we form a carbocation or radical. Or a lone pair. In all cases, we can get a resonance structure with these compounds. Make sure I'm not running off the board for you there. So we can create a resonance structure. Looks like this. Or we can create a resonance structure. It looks like this. Or we can create a resonance structure. It looks like this. The idea here is that because the allylic carbons are adjacent to this double bond, they participate in resonance structures with the double bond. And inherently having a resonance structure makes you more stable. So if we have a radical, a carbocation, or an anion sitting on an allylic carbon, it's more stable. So this means then that if we want to react off those hydrogens, and we can do so in such a way that forms a carbocation, forms a radical, or forms a lone pair, we're more likely to do so than say something like this methyl group. So if we pull a hydrogen off this methyl group and form lone pairs, there's nowhere for these lone pairs to go. If we form a radical, there's nowhere for the radical to go. If we form a carbocation, there's nowhere for that carbocation to go. So these allylic carbons here basically are stabilized for hydrogen abstraction. So if we want to replace the hydrogen, and typically we're going to do this through by creating a lone pair or creating a carbocation or a radical, it's much more stabilized. Now, to also give you a flavor for Orgo 2, let me just erase this. We have a diene. we decide we want to do Hbr addition. And our first attack here is with a bromine. Or no, we're going to have our first attack by from the double bond on the hydrogen. So as a first step, this will attack the hydrogen, which will give us a carbocation and a hydrogen. Well, we could have the bromine react in this case with this carbocation, and we end up generating this product. But this is also an allylic carbon now. So when we break up that double bond, we can resonate, and we can get the carbocation to move down to the next carbon. And in this case, we would get this product. So this is the 1,2 addition. This is the 1,4 addition. And they're called by chemists, and I really hate this because it's not the correct way to describe it, but whatever. This is called the kinetic product, and this is called the thermodynamic product. So because of these allylic carbons, we can actually explain why we get different products if we have dienes, and why we can control at low temperatures we get the kinetic product, where at high temperatures we get a mixture of the thermodynamic and kinetic products. But yeah, you don't even know this level, but this allylic carbon does come back in Orgo 2. Actually, for the test 1 material, we start talking about kinetic versus thermodynamic products, dienes, and things like that. But yeah, glad that helped. Move that real quick. It's fine if you don't have questions today. Like, we're kind of getting towards the end of the material. You're getting, next week is, I think, your exam, or when your exam would be, just basically when the homework is due. Yeah, again, I kind of like to front load courses if I can, so I think I did a really good job of that this semester, where I front loaded the material, so now it gets progressively easier and easier. I'm still weighing what to do with the final. I still like the idea of making your homework your exams, but it does need to be a cumulative exam. So odds are what I'll do is I'll create another assignment that's the review material, and that'll be a certain percentage of the final exam grade, and then you've got the homework, which is the other percentage. But I'll give you more details about that as it comes out. Next week, you have the really fun discussion board. My opinion, it's a fun discussion board with the extra credit for anyone who figures out what the product is or the precipitate is in the reaction, and you'll see the full reaction scheme. Week after that, you're going to have a lab practical review discussion board. Your only obligation is to ask me whatever questions you have, but I'm going to tell you in that discussion board what you need to know for the lab practical. The practical itself will be given online. So you'll have a week to complete it. During that week, you need to take it, do it, and then the week after that will be the week of exams. Now, with the week of final exams, you're going to have the full week to take the exam. You're going to notice the cutoff on Blackboard is going to be at 3:01 p.m. on Friday. That is for my sanity. You get an hour and 50 minutes to take the test. The grades are actually due the following Monday. So when it comes to the final exam, yeah, you technically had the full week, but that 3:01 p.m. cutoff means that you can't start the exam after 3:01, which means you won't be able to finish it any later than 5 p.m. So yeah, if you're good, we can sign off. There's no obligation that this needs to take a full hour and 15 minutes. So we are technically in an online course, and it's very rare that online courses would even have these typically long live streams. But yeah, we also recognize instructors, you didn't sign up for an online course, you sign up for a seated course. So this is the closest we're going to get. So yeah, if you guys are okay with signing off, if I don't hear any objections in the next 5 minutes, we'll just sign off. This should just be a short live stream for today. Do make sure you're doing the homework. That is your exam. So that is going to be your exam 4. You are free to ask me questions about the homework. It's not like this is meant to be, you have to do the homework entirely on your own. Particularly don't use up your submissions. Ask me. I've already had one student this semester. They were answering the question correctly. They were just putting it in formatted incorrectly. And I would rather you get it wrong because you don't know it than you to get it wrong. You knew it, but the formatting was wrong. So that's a big thing I can check on my end, is to make sure that the formatting of your answer is correct. And if you get it right, I'll tell you it's right. Like, I'm not going to like keep that from, I'm not going to say, ooh, the formatting's wrong, but did you do it right? I'll tell you did it right. All right, so your 3 are the only people that are logged into this live stream. All 3 of you said you're good to go. So I'll sign off. Thanks for showing up today. Again, if you got any questions, please feel free to email me. During the lab time today, I'm going to be available via Teams and email. So I'm prepping my 152 exam today, so I'm definitely going to be by my computer. Nice seeing y'all, and hopefully I will talk to you next week.